In the previous lesson, we introduced what matrices and vectors are, we covered typical notation that we use for them, and we looked at some basic operations. In this lesson, we will look at examples of matrix multiplication. So this is an operation that we did not discuss in the previous video. I will introduce the most standard presentation of the algorithm used to multiply two matrices together, and then we will look at some basic algebraic properties. We'll do some example exercises where along the way I will introduce in a few more named special matrices so that we're collecting kind of a family of recognizable types of matrices. And then I will end this video with a brief note about what A times EJ is, where EJ is a standard basis vector. Okay, so let's first talk about when it is possible to even compute a matrix product A times B. A and B can be rectangular arrays, and what must be the case in order to multiply them together is that their inner dimensions must match. So in this notation here, A sub m times n and B sub n times p, the inner dimension is the n for both of these matrices. In other words, the number of columns for A must be the same as the number of rows for B. In this particular example, A is a 2 by 3 matrix and B is a 3 by 2 matrix. Since the inner dimensions are both 3, we could multiply these two matrices together, and we will do so in a few minutes. The product AB will be a matrix in its own right. The dimensions of the product will be the outer dimensions. So the number of rows for A and the number of columns for B. In this particular example, A had 2 rows and B had 2 columns. So the matrix AB that we will compute in a few minutes should be a 2 by 2 matrix. When I first learned how to multiply matrices, I was probably 10 years old or something like that, and we did not phrase it as a dot product. But I would like to do so here. If we can say how to get any entry I sub j in the matrix product, then we know how to multiply them together. So what is the ijth entry of AB? It comes from taking the dot product of the ith row of A with the jth column of B. So if you think of the ith row of A as a vector, transpose it to be a column vector and dotted that with the jth column of B, dimensionally you can do that because of the matching inner dimensions, and the computation would produce the sum that we're looking at here. Okay, so let's do this example. In order to get the entry in the 1, 1 position of AB, I'm going to take the dot product of the first row of A and the first column of B. So that looks like taking 1 times 7 and adding to it 2 times 9 and adding to that 3 times 11. Moving over to the right, in order to get the entry in the position 1, 2, we will take the dot product of the first row of A and the second column of B, and then coming down to the second row, the entry in the 2, 1 position will be the dot product of the second row of A and the first column of B. And to finish this computation, the entry in the position 2, 2, the second row, second column of the product, will come from taking the dot product of the second row of A and the second column of B. Okay, the numbers here are actually quite large, so you might want some computational aid to do that. But the matrix we get from multiplying A with B is this 2 by 2 matrix, whose first row is 58, 64, and whose second row is 139, 154. Just to make sure that you followed that, or that if you've already seen matrix multiplication before, that you're all set to go, take a moment to pause and work through this exercise. I would like for you to first identify the dimensions of the two matrices being multiplied. Then once you acknowledge that multiplication here even makes sense, it's possible to do it, identify the dimension of the product. So what size matrix will we produce? And then go ahead and compute the product, or at least a few entries of it. Make sure that you understand how to get the resulting matrix. Okay, here are the solutions. The first matrix is 2 by 3, 2 rows, 3 columns. The second matrix is a square matrix. It's 3 by 3. We have matching inner dimensions, so multiplication is possible, and the result will be a 2 by 3 matrix. And then if you compute it out, the first entry in the top left corner will be 1 times 2 plus 5 times 3 plus 7 times negative 2. That should give you 3. And then here are the rest of the entries in the 2 by 3 matrix. Let's do some more exercises. For these 10 expressions, what I would like for you to do is imagine that A is a 3 by 7 matrix, B is a 3 by 3 matrix, X is in R3, Y is in R3. Some of what I've written down here might not make dimensional sense. So if that's the case, just write DNE for does not exist. Otherwise, provide the dimensions that we would get after computing the matrix product. At this moment, pause and work through these 10, and then I will present the solutions. Okay, let's see if your answers match mine. For the first one, can we multiply A times B? And the answer is no. This matrix product does not make sense because the inner dimensions do not match. The number of columns for A is 7, but the number of rows for B is 3. On the other hand, we can do B times A, and the result will be a 3 by 7 matrix. We can also do A transpose B. Recall that A transpose flips A. After flipping it, it will be a 7 by 3 matrix, which can be multiplied with a 3 by 3 matrix, producing a 7 by 3 result. We can also do B transpose A. That would be 3 by 3 times 3 by 7, giving us a 3 by 7 matrix. And in a moment, we will talk about how the matrix we would get from exercise 4 is the transpose of the matrix we would get from exercise 3. But before we do that, let's finish the rest of these. B times X makes sense. 3 by 3 times 3 by 1. Remember here that X and Y saying that they are vectors in R3 means that they are columns. The result will be a vector. It will be a 3 by 1 vector. Now that we've recognized that X is 3 by 1, XA makes no dimensional sense. On the other hand, we could transpose X and then multiply it with A. Transposing X would turn it into a row, a 1 by 3 row. Multiplying it with a 3 by 7 matrix will give us a 1 by 7 matrix. In exercise 8, writing multiplication of two vectors this way does not make sense. So saying X times Y, where the action of times there is matrix multiplication, is not a legal operation. You can't do that with two 3 by 1 arrays. If you wanted to do the dot product, you would need to write a dot between them. Unlike with regular multiplication, the dot in a dot product is not optional when you write it down. Another way to do a dot product, though, if you do want to write it as multiplication, is to say X dot Y is actually the same as doing X transpose times Y, where we pass from a dot product to a matrix product. So in number 9, X transpose Y will flip X into a row. We will have a 1 by 3 matrix times a 3 by 1 matrix. The result will be a 1 by 1 matrix. We could just call that a scalar. And it will be literally the dot product of X with Y. So anytime you want to do the dot product of two vectors, you either need to write X dot Y or write it as in number 9. What happens if we transpose Y instead? X is 3 by 1, Y transpose is 1 by 3. This will actually produce a 3 by 3 matrix. Let's talk about exercises 3 and 4 a little more. So a moment ago, I alluded to the fact that A transpose B transpose, the transpose of that product, is the product of their transposes but in the reverse order. So it would be B transpose A. It's a fun exercise to show that this equality holds. To do so, let me think about what the individual coordinates in the matrix on the left look like. So in other words, if I think about A transpose B transposed in terms of the ijth coordinate, then the first thing I want to recognize is that I can write this as the jith coordinate of A transpose B. Okay, so I'm undoing a transpose by reversing the rows and columns. Now I'm saying, given the matrix product A transpose times B, what would be the jith coordinate? By definition, that would come from taking the dot product of the jth row of the matrix on the left with the ith column of the matrix on the right. So in other words, the jth row of the matrix A transpose with the ith column of the matrix B. Now let me transpose each of these individually. So in other words, the jth row of A transpose is the same as the jth column of A. It's the same entries. And likewise, the ith column of B has the same entries as the ith row of B transpose. So here when I say equality and I'm saying that things are the same, whenever I write a vector dot product, I'm imagining two proper column vectors. And in these expressions, I'm saying where the entries in those column vectors come from. Vector dot products are commutative, so let me just flip the order here so that on the left we have the ith row of B transpose, those coordinates dotted with the jth column of A. Take a look at that and see if you can anticipate what's coming next. After this rearrangement, what we are looking at is the row from the matrix on the left with the column from the matrix on the right. That is exactly how we define matrix multiplication. So this expression is equivalent to the ijth coordinate of B transpose A. So since we can now conclude that the ijth coordinate of the expression on the left, the transpose of A transpose B, is equal to the ijth coordinate of the expression on the right, B transpose A, those two matrices must be the same. Here's the general principle. Just switching letters here not to mix up with the A and B that we were just working with. If U is an M by N matrix of real numbers and V is an N by P matrix of real numbers, the transpose of their product is the product of their transposes in the reverse order. What I would like to do is take a moment to just work through their dimensions, and what I would like for you to take out of this is that anytime you are doing mathematics where you're mixing scalars and vectors and matrices, really anytime you're working with matrices, always identify the dimensions of the objects that you're working with. It's an excellent habit to develop. So if I take U times V, we know from looking at their outer dimensions that that would be an M by P matrix, but I need to transpose it. So on the left, we have a P by M expression. On the right, if I'm just annotating this computation, V transpose will be P by N. Let me first write it's an N by P matrix transposed. Likewise, U is an M by N matrix transposed, taking us to the product of a P by N matrix with an N by M matrix. The inner dimensions match, and we would end up with a P by M matrix as expected. So there was nothing new here really communicated, but please always take a moment to look at the dimensions. Okay, so one property of matrix multiplication is how the action of transpose works. Let's talk about a few others. So for each of these expressions, assume that all of the respective inner dimensions match so that the multiplication makes sense. Then matrix multiplication has a lot of nice properties. It's associative. A times the product of B and C is also A times B, that product times C. That's associativity between, say, 3 arrays. For a scalar out front, you can actually just pull that through the computation however you want. So the scalar lambda times AB is the same thing as first scaling A and then multiplying that with B, or alternatively, you could first scale B. Okay, so you can be pretty casual with scalars and where you place them in a matrix product. Matrix multiplication is also left distributive and right distributive, as I've written out here. So A times the sum of B and C is AB plus AC. And similarly, if I take A plus B and multiply that from the right with C, that is AC plus BC. These properties should remind you a lot of kind of regular multiplication between numbers. However, matrix multiplication does not have commutativity. That is almost always the case for two matrices A and B. And in fact, as we've seen, sometimes A times B dimensionally makes sense and B times A doesn't even make sense. But even when it does, it's not necessarily the case that you can reverse the order. So always respect the order of matrix multiplication, reading left to right. Let's talk about square matrices in particular. So these are matrices with the same number of rows and columns. Square matrices are a bit special. So one thing that's special about them is that they have a multiplicative identity. The identity matrix that we introduced in the previous lesson acts like the number 1 when you multiply it with a square matrix. Since square matrices have just the same dimension for rows and columns, you can take a square matrix and multiply it with itself any number of times. We would call that matrix exponentiation here. So the square matrix A raised to the nth power, you want to think of that as A times itself n times. While square matrices have a multiplicative identity, they do not necessarily have a multiplicative inverse. So what I mean by multiplicative inverse, if we look at just numbers, the multiplicative inverse of the number 4 is the number 1/4. And on the other hand, the multiplicative inverse of 1/4 is 4. Square matrices do not necessarily have a partner like that, but sometimes they do, and when they do, we say the matrix is invertible. So formally, if for some square n by n matrix A, there exists an n by n matrix B, so that A times B is the identity matrix and B times A is the identity matrix, then we say that A is invertible, and we would normally name this matrix B as A inverse. Read that as A inverse. Don't read it as 1 over A. Division by matrices doesn't make sense. So that exponent here is indicating a multiplicative inverse, not division. Rereading this through the lens of looking at the matrix B, B is also invertible, and its matrix inverse would be A, which you could name as B inverse. Here I've written that AB and BA must both be the identity matrix, but actually it's enough to just know that AB is the identity matrix. You don't really need to check BA, but proving that is hard at this point in our discussion. Let's do some more exercises, and I'm going to introduce in a couple more families of matrices. So these are some named matrices. Take a moment to compute A times B if A is the upper triangular matrix I've given you here, and B is also an upper triangular matrix. So hopefully looking at these, you understand what an upper triangular matrix is. It's one where you only have 0 below that main diagonal, which starts in the top left corner. After you've done exercise number 1, or at least enough entries to kind of see what's happening, fully do exercise number 2. It won't take you as long. So here I've given you what we call diagonal matrices. D1 is the diagonal matrix with 2, 3, 4 along the main diagonal. D2 is the diagonal matrix with 5, 6, 7 along the main diagonal. So diagonal matrices are always matrices where you have 0 off the main diagonal. Compute both D1, D2 and D2, D1. So flip the order. And then after you've done that, tackle this third exercise. So just think about this question. If A times B equals A times C, does B necessarily equal C? In other words, do we have a sort of cancellation law for matrix multiplication? Now that I've read through these 3 exercises, please pause and think about them before I reveal the solutions. All right, for number 1, I'll be really impressed if you worked through the entire thing by hand, but the resulting 3x3 matrix that we get is upper triangular. And that's not a coincidence. So the product of upper triangular matrices is itself an upper triangular matrix, and you'll notice the main diagonal consists of the products of the respective diagonals. That's also what we see in exercise 2. So when you multiply 2 diagonal matrices, you simply multiply their diagonals, and since it just comes down to that, here's a case where matrix multiplication is commutative, but again, that's very rare. So in those 2 exercises, I wanted to just define an upper triangular matrix and also a diagonal matrix. If you're wondering if there's such a thing as a lower triangular matrix, the answer is yes. Those would be 0 above the main diagonal. The answer for number 3 is no. Matrix multiplication does not have cancellation. If it happened that A was an invertible square matrix, then you could take the equality AB equals AC and multiply it from the left by the inverse of A to basically cancel out A. Otherwise, the statement is not true. So here's a counterexample. Look at these 3 2x2 matrices and not only recognize that AB equals AC, but try to think about how I came up with this counterexample. Let me give you a tip. Whenever you are experimenting with matrices and perhaps you're trying to generate a counterexample as I was doing here, be friendly to yourself and bring in lots of zeros and also lots of instances of the number 1. So 0 and 1 are the easiest numbers to work with. That will make your life better. So what I did was I made A mostly 0 with just a 1 in the top left corner because I recognized that that number 1 would only meet certain entries from B and C. The entries in the second row of B and C will just be hit with the zeros from A. So I could make those different. Okay, so I wanted to give you that general principle. When you're playing around with stuff, try basic looking matrices with lots of zeros. We are going to wrap up this particular video with a remark that will carry into our next video, and that is I want to talk about what it looks like when you take a matrix and multiply it with a standard basis vector. So recall the standard basis or canonical vectors for, say, Rn is a family of n vectors, which are mostly 0, except for a single 1. So E1 is 1, 0, 0, 0, 0, 0. Just to experiment until you recognize what's going on, let A be this 3x4 matrix. Since it's 3x4, I'm going to multiply it with vectors which are 4x1, so vectors with 4 entries. Take a moment to check what A times E1 is, where here E1 is 1, 0, 0, 0, needs to be a vector in R4. Likewise, what is A times E2, E3, and E4, where each of those are vectors in R4. I hope you recognize that what happens is anytime you take that matrix A and you multiply it with one of the standard basis vectors of R4, what it does is it returns you back the respective column from A. So A times E1 produced the vector 1, 2, natural log of 2. That's a vector in R3. A times E2 produced 2, 3, 0. A times E3 produced the third column of A, so 1, 0, E. And lastly, A times E4 returned you the final column from A, 0, pi, and 10. I will wrap this video up here, but let's keep working with this idea in the next video. Thank you for your attention.